Okay, I hope you've had a chance to look at this and maybe draw the AC circuit here. This will give you a chance really to sort of see how you're doing. So here we are back again. Here's the model for the transistor right here. Base, emitter and collector. We're just asking the question. Now let's look at this. What's connected to the collector? I've got a 10K resistor there, other side of which is connected to the ground. So here is that 10K resistor. Alright, I'll show that, 10K. Alright, now look also what is connected to the collector. I've got this capacitor, AC-wise appears as a short, so the collector is also connected to another 10K, which is also connected to the ground. So I have another 10K resistor sitting there. The voltage, the output voltage, of course, is at the collector with respect to the ground, like so. Let's go to the base side. On the base, I've got this 10K resistor connected to ground, so let's draw that guy in like so. There it is, 10K. Also, the base is connected what? 100K on one side. The other side of that 100K AC-wise is connected to ground. So there it is, like so. There's my 100K resistor. Capacitor appears as an AC short. So there it is, an AC short. And then I've got a 1K resistor sitting here. And then I've got my signal source sitting here like so, which is Vs. Okay, so there is my AC equivalent circuit. Now this is more involved compared to what you've had before, and it's more involved because of the presence of this resistor. It's more involved really because of the presence of this resistor, which could be some signal source resistance. And I may end up losing some of my signal really across that resistance. Okay. Now what we want to do is we want to just tidy this drawing up a little bit. Let's combine these two resistors which are in parallel. Let's combine these two resistors which are in parallel. The combination of these two, we've done this before, that's a 9.1K if I combine those two. And of course a 10K in parallel with a 10K would give me what? Well, that would really give me a 5K resistance if I combine those two together. Okay? So let's go ahead and do that and redraw the circuit. Okay, so I have now redrawn that circuit. Here's my Vs, here's that 1K resistor. I've combined these two parallel resistors, that's the 9.1. Here's my transistor AC model here, the 1K emitter resistor, and then I combined those two 10K resistors, and there's the 5K. Alright, I'm trying to find that voltage over that voltage there. Now how do I do this? Well, it looks a little bit tricky, okay? Now, why does it look a little bit tricky? Now, this side is pretty easy. Look, what's the current in the 5K resistor here? Well, it's this beta IB, isn't it? There's IC flowing like this, okay? Adds to IB, so I've got IB flowing here, I've got IC flowing here, that's IE, and then IB flowing this way, and IC flowing this way. So yeah, I know this. I know that there's beta IB current flowing in that 5K. That's easy. I can work out that voltage in relation to IB very easily. But look, this is the tricky bit, right? This is really the tricky bit over here. I can't take a simple loop here. I could take a loop here, I could take a loop here, but it looks tricky. It wasn't like before I had one nice loop I could consider, and I could easily get IB in terms of Vs. This is a bit more tricky because of really this kind of T-section that you're seeing right here. So how do you think you could maybe simplify this circuit? Is there a way you could simplify the circuit? Well, often when we have these T-type sections, one way to simplify that is what? To really take the Thevenin equivalent. So really, I could take this, couldn't I? And I could replace that, as it were, with the Thevenin equivalent. And what does the Thevenin equivalent look like? Well, it's going to kind of look like a source here, all right, which we'll say is V Thevenin in series with a Thevenin resistance. Okay, so really I could replace this with this. Okay, so I have to find the Thevenin equivalent. How do I find the Thevenin equivalent? Well, I remove the load. This guy then is the load. Okay, so I'll just disconnect. Okay, and what am I left with? If I disconnect, I'm just removing the load. So let's do that and see if we can calculate then the Thevenin equivalent. All right, so here you go. I'll take the load off. That's one way I can show you that I'm taking that load off. Okay. All right, so what have I got? The Thevenin voltage, that's the what we will call the open circuit voltage, right? That's really the voltage really right here. That's the Thevenin voltage, plus minus. What is that voltage? Well, it's what? The Thevenin voltage would simply be, there's V Thevenin. It's going to be equal to what? It's going to be 9.1K, right? So we'll say it's 9.1K divided by what? The sum of the two, which is 9.1K plus the 1K, times what? Times, basically, if you like, Vs. Okay? That's the Thevenin voltage. And we'll evaluate that in a second. The Thevenin resistance is resistance looking back in here with all internal sources set to 0. So if I set that voltage source to a 0, I replace it with a short, and I see 9.1K in parallel with a 1K. And so I really could say the Thevenin resistance is really nothing more than 9.1K in parallel with 1K. All right? So if we evaluate that, what do we have? If I evaluate this, the Thevenin voltage then is simply equal to, and that's 9.1K divided by 10.1K of V of S. So it's simply going to be equal to a 9 or 0.9, I should say, Vs. So V Thevenin is 0.9 Vs. If I evaluate R Thevenin, I've got to remember these two in parallel, that comes out to be 900 ohms. So a relatively easy calculation to get V Thevenin and R Thevenin. I can now replace this with this. Okay? Okay, here I've now redrawn the circuit. Here's my Thevenin voltage right here, which was what? 0.9 Vs. Here is the Thevenin resistance, which was 900. Here's the 2K resistor, or rather the transistor model sitting over here. Here's the 1K emitter resistor, and then that's our 5K combined resistors on the collector side, okay? This is a much easier circuit to now deal with. It really is. It becomes really a loop type problem, okay? A loop here, and of course we know the current in the output, or rather the resistor over here, the 5K resistor. So we can get the output pretty quickly. Let's do that. The output voltage then is equal to, what's the current in there? It's beta IB. So it's beta IB times 5K. Remember, I'm measuring the voltage though, plus minus. That's how I'm measuring it. So I have a minus sign sitting in front. Okay. On the input side over here, really what we're going to do is take a loop. So let's just go around the loop here, okay? Look at the polarities. What are the polarities? Plus, minus like so, plus, minus like so, and plus, minus. So let's go around that loop. I've got this voltage here, which is the Thevenin voltage. What is that? 0.9 Vs. This voltage here, which is what? Minus IB times 900, okay? This voltage here, which is what? A minus IB 2K. And then this voltage here, which is a minus IE 1K, and all of that is equal to 0. So there's my basic loop, okay? Remember, that's the output voltage. All right, so what we're going to do is take the IB terms over to the other side. All right, so let's go ahead and do that. I've got 0.9 Vs, that's the Thevenin voltage, okay, is equal to, what is it equal to? I've got 900 IBs, so there you go, 900 IB. Okay, I've got what, 2K IBs, so that's a plus 2K IB. What else do I have? I have this guy here, right? Well, IE, remember what IE is again? 1 plus beta IB. Okay, so we might as well just put that in. Okay, so that's a plus 1 plus beta times IB times the 1K, all right? Remember, that's the IE term there, all right? All right, so now look, you could add all this up. Look, I didn't put a number in here. You can do that. Beta's 100. That's 100 plus 1. That's 101K IBs there. Plus 2K, that's what? 102, 103K right? Okay, add the 900 to this. What have you got? Okay, you've basically got 103.9. So therefore, I can say 0.9 Vs is simply equal to 103.9 K times IB. All right, so we're getting pretty close, okay? I've now got basically Vs in terms of IB and Vout in terms of IB. So what we're going to do now is take the ratio. So what have we got? We've got VO over 0.9 Vs at the moment, and that is equal to what? Let's just put it in. That's a minus beta IB times 5K divided by this term here, which is 103.9 K times IB. We're nearly there, okay? The IBs will cancel there and there. I can take this 0.9 to the other side, and so I have VO over Vs is equal to a minus 0.9 times beta times 5K, and that's divided by 103.9K. If you care to evaluate this, this comes out to be a minus, approximately a minus 4.3 as a voltage gain. So what you've been able to do here is really take a relatively complex circuit. You've been able to simplify it using Thevenin, and you've really boiled it down to just being able to take a simple loop here to get basically IB in terms of Vs. Okay?